Alright, let's get started. Alright, welcome everyone. Today we have ELMO 2013 problem 6, which goes as follows. You have a function f from z to z, and what the problem is trying to say is that most of the time Cauchy's functional equation is true, by which I mean explicitly for every n, if you look at ordered pairs x and y with absolute value at most n, then 99.9% of the time you have f of x plus y equals f of x plus f of y. So that's true. And the question is asking, okay, is it possible that for some for some non-negative n, f is not linear for like more than half of those inputs. So basically, if this equation was true for every x and y, then you expect f of x to be a linear function, i.e. f of x equals x times f of 1. But here the problem is giving you like the 0.1% of the time this assertion is allowed to be false. And the question is, can it be false can this cause the function to be eventually non-linear for some very large n? So it's a bit of an involved statement, but it's essentially saying you have certain non-linearities and you would like to see if the function is still mostly linear. So, I'm gonna introduce some terms right away. We'll say a func, then the integer a. N is good if f of n equals n times f of 1. So 1 is automatically good. And we want to show that there's not too many bad integers. So the data that we have is that like if x is good and y is good. So let's also say a pair xy is good if it satisfies the Cauchy functional equation. So x is good and y is good implies the pair xy is good. So to be clear, there's two adjectives I'm using here. It's like good can be used to describe a single number, it can be good or bad. Also a pair unrelatedly can be good or bad. And you want to show if there's at most 0.1% bad pairs, does it follow that you don't have too many bad numbers? So good is good bad is bad. But if x is bad and y is bad, this could go either way. However, also all the numbers from so the first time you possibly run into bad integers is like what, 32? So all the numbers in minus 31, 31 are good. So we have enough base cases is what I'm trying to say. Alright, now what? So let's see. I actually think 32 should be good as well, because if 32 is bad, that causes a lot of bad pairs to show up. Yeah, the problem is if 32 was bad, then you automatically get a lot of bad pairs. So the first bad number is in the thou. I don't know if it's thousands. No, it is thousands. So when's the first time a bad number can show up? If n is bad, then the number of bad pairs for that particular threshold is at least 2n minus 1. No. 2n minus, yeah, 2n minus 1, 2 times. Yeah, all those pairs are now bad. No, wait, hang on, something's weird. You can, like, x plus y, this x plus y is bigger than n. So... Sorry, this analysis doesn't make sense. I don't know what I'm talking about. I need the negative numbers. Yeah, sorry, this analysis is wrong. X plus y, x plus y good. X plus y, x, y good implies x, y good. And exactly one of x plus y, x, y bad implies x comma y is bad. So I am not totally sure about this condition, what I just said. So 0, 1, minus 1 are definitely good by definition. Yeah, so up until, okay, it should still be the case that minus 31 to 31 is good. Because up until... You just can't have any badness early on, I think. Let me show this. So, I know if I look at 1, 0, minus 1, and there's 0, comma 1. Okay, let me carefully think my way through these things. 1 is all good by definition. 1, 0. Okay, sorry. Every pair up until a certain threshold is good. So 1, 0 is good, hence 0 is good. And f of 0 equals 0. Okay, and the same thing this should just work in general. So if 1 through n are good, then 1 comma n means f of n plus 1 is good for most n. Yeah, okay. So up until minus 31 to 31, I think everything was good. And then in general, up until minus n to n. Okay. Yeah, so the point is that there's some negative numbers that can bring you down into a better place. So the first problem issues are going to happen like... How are the AMC operations this year? About normal. I think I haven't heard much, but I haven't been paying that much attention either. The problem is once I introduce a blip, Like at the first point in which I have a bad number, that number will continue generating bad pairs for a long time after that. Yeah, I think the trick is I was thinking xy positive in my head, but I definitely want y is negative, I think. So yeah, I wonder if I can show like the proportion of bad numbers never goes worse than a certain threshold. Can both x and minus x be bad? Yes. How do we know minus 31, 31 is good? If you have any bad numbers in there... Yeah. Oh yeah, that's an interval. No, I'll make this. I think the other thing that's interesting about this problem is that the x plus y can be outside the range. So it's actually quite hard, I think, to get your first bad number. Because if m is the first bad number, you actually run into issues when n is strictly less than m. Like that number won't. So it's sort of like, as each step, the fact that a number is good forces numbers later to be good, or something like that. So it's not like it can sort of see ahead. Yeah, minus 32. Yeah, yeah. I'm just like this man's very dumb. I wonder if the 1/2 matters. Like. No, so here's the thing. 32 is good for sure because 16 comma 16 must be good because that interval no, we don't. Shoot, is it 16? 16 16. Yeah, it's barely off. So 32 could potentially. Sorry, I messed up. That's outside our range. 15. But see, here's the reason 32 is good. Like 16, 16, 15, 17, 14, 18. is 3 pairs. You can have at most like a small number of those be bad. So that's the reason 32 is good. Yeah, so it's so strange. Like, it's the fact that x plus y lies outside the place that you're testing. Like, you're testing absolute value x, y, and most n, but this x plus y lies outside absolute value n. So yeah, this will get up to yeah, pretty. So I have this thought that like maybe what I want to do is say like yeah, I feel like I want to draw pictures. I thought this was going to be like a functional equation, but I don't think it is anymore. I think this is more like draw some pictures and see what happens. I still have not cleared the whiteboard yet from... I really need to do that. Alright, one moment please. Yeah, the whiteboard is actually overflowing with stuff because I keep forgetting to do maintenance and clean it up. Oh, actually, it would be interesting if at least, yeah, you could make a statement like at least one of x and minus x is good. That feels a little optimistic to me, but not unreasonably so. Like, I would be surprised, but I wouldn't be, like, shocked. Alright, so I need to... People want to watch the process. It's like... There's like, I don't know how many streams worth of stuff. I need to... Okay, so that's like TSTST day 3. And which one was the one with sure? 48. Okay. Okay. Wow, this stuff is ancient. This is from TSTSD Day 2 stream. Alright, we're almost there. We appreciate your patience. Something. I don't remember which stream this was from. You know, let me just. I think this is so long ago. I'll just grab them all. Okay. That's that. Okay, so I wonder if I want to draw the picture. I don't know exactly how I want to draw the picture yet, to be honest. Yeah. Well, I think if you want to do an induction type thing like this, you want to assume that like up till n is not too bad or something like that. Like the 1/2 bound seems really not good. Like if it's deteriorated that much, we're in trouble. So if this threshold Thank you, 3234 for the follow. Like, suppose I looked at this number n plus 1 or something, right? Like, this is 1 plus n, 2 plus n minus 1, and so on. So, if I, in general, whenever I have a bad number, if like n plus 1 is bad, then in here there's at least one bad number every pair, or something. Like, this interval. Yeah, actually, wait, that's really heavy. Like, it's like for every 1 in n, 2 in n minus 1, and so on, there's at least one. There's either a bad pair or a bad number for each of these. Evan, did you buy any shares of GameStop? No. Okay, so what if I like let's draw a thing where I don't freaking know. You imagine writing up triples such of a plus b equals c, like something like this or something. Yeah, then certain numbers are bad and certain pairs are bad. And what we know is that anytime there is there's like a bad, if you have a bad pair, then inside there must be a bad number. I don't know if it does anything. Initially, all pairs are good. Then, at some point, you can have a bad. So let's see. We know that, let's say, like all the numbers from 0 to like, we have all good numbers for a while, and then eventually you have your first bad number, which will cause, I think it can't happen until like 2000 actually. So this causes a bunch of bad pairs. 1, 1, 9, 9, 2, 9. The 0 2001 pair, ironically, is actually still good. This will also cause 2001. Wait, this generates a lot of bad pairs. I mean, it's only off by constant factors. I'm just trying to be careful or something. So I think I actually need to go up to this. Generated like 2000 bad pairs out of. Oh, actually, no, this is okay. So that's, suppose we have that as our first bad number eventually. Then. I mean, you can imagine if I replace 2000 with a million, and then I can have just like 3 consecutive bad numbers or something like that. So. The problem is eventually when you get to like a high enough density or something. Like some these things are more asymptotic, and right now I'm doing things that are still too precise. So in general, suppose I have like g is the subset of good numbers in minus n to n, which I want to always be like pretty dense. So g plus g, the set of numbers is a subset of minus 2n comma 2n. The number of surprise. Hey Bobby, good to see you. Please help me out here. I'm gonna die. So you get this, and then for every number, like I want a result that says if g is at least n halves, then like, I don't know. If g has a lot of elements, then there are a lot of pairs that are do something. I don't know. I don't know what that something is. Thank you, Toyon, for the raid. Alright. So, hi everyone. For people who haven't come here before, my name's Evan. Thank you, Hanikos, for the follow. I stream competition math every Friday night starting 8 p.m. Eastern. Typically, we do random competition problems that my viewers send to me until I get tired, and then I go and play games for the rest of the stream. Yeah, thanks for coming by. The problem we're working on right now is up here. Yeah, feel free to help me out here because I'm not getting anywhere right now. Thank you, Miss KE, for the follow. How's it feel studying at MIT? I really like the place, yeah. I did my undergrad at MIT and it was a lot of fun. Thank you, Sachi Papas, for the follow. Yeah. So I think the first bad number has to be like the first bad number actually generates a lot of bad pairs. Let me just try to take a summary. So from with xy in minus n to n, there's a total of it's like 4n squared-ish pairs. So x plus y ranges from minus 2n to plus 2n. There's a certain number of pairs that stay inside the interval, and some of them will land outside. Alright, good night, Mixed Linear. Thanks for stopping by. Like the problem, yeah. I'm not sure I'm gonna finish this one, to be honest. I feel like, well, I don't know. $19.99 plus 1. There's some kind of analysis problem. It feels pretty combinatorial to me, to be honest. Like, I think it's saying something about the structure of the addition. Yeah, it's a completely discrete problem though. G for minus n to n. Yeah, like somehow it's sort of something like if all the numbers are bad, then we're dead. So we do need a base case. Like somehow the fact that the first many numbers are good, and then we need to claim that the I don't know if it's the density is what I want, but we need to claim something doesn't grow too quickly. Or not grow. Something stays goodish. Like I need to somehow say like, okay, at the beginning everything is good because 0.001 n squared will actually be strictly less than 1 for n up to like 30. And then yeah, I actually do like the dyadic induction that was suggested earlier. Like this idea like, okay, we'll say that density is so and so for minus n to n, and then you expand it to minus 2n to 2n. But I don't know exactly what that argument would look like, or I don't know what would happen. I guess I could just try to like force in, see what happens. Um, so I'm just gonna try to be heavy-handed. So let's say that only epsilon n bad numbers inside here. So there's a few bad ones, but not very many. Then what can I say about the outside? Uh, so for a number that's outside, there's a bunch of... I don't know if I want 2n, but if I go like n plus 1, the n plus 1 is the strongest thing I have right now, to be honest. It's like n plus 1 is involved in a bunch of pairs. It's like there's a 1 to n, 2 to n minus 1, and so on. So like, yeah. Do some people in the chat know a proof? No. The point of this stream is that no one actually knows how to solve any of the problems, and we slowly try to work it out. With varying amounts of success. What was beginning like in competition? I don't. It was a long time ago. I was in middle school and I was doing MathCounts or something like that. Okay, here's what I'm going to do. I'm going to look at the pairs, like 1 plus n, 2 plus n minus 1, and so on, up till like, let's say like n over 2-ish. N over 2 plus n. This is like n plus 1. So we're going to go up to like 3 halves n. When I do this, we're assuming there's only epsilon n bad numbers. So like a small fraction of these numbers are bad. Each number appears how many times? Well, okay, n over 2 appears every time. That's okay. So each number appears up to n over 2 times. Sorry, I drew this wrong as well. I don't want a triangle, I want a trapezoid. So this is a trapezoid. And that goes up to like n plus n over 2. So there's like n over 2 guys here. And yeah, this trapezoid shape. So every bad number appears up to n over 2 times. It can appear once per column. So up to a constant fraction of these numbers are bad. On the other hand, yeah, so at most epsilon times, let's say I circle the bad number, so maybe the number 2 is bad or something. So here's a bad 2, here's a bad 2, whatever. Actually the whole row is bad. Did they appear? No, they appear twice. I wonder if I want to just make it a rectangle. Square. Would it be easier if this is a square? I think it's simpler if it's a square. Screw it. Alright, change of plan, guys. We're making a square. Okay. So 1 plus n, 2 plus n minus 1, up to let's pretend like n is odd. So this is like n. So it'll split cleanly. Or not odd, even? No, odd is better. Okay, and then this is 2 plus n minus 1 up till n minus 1 halves plus n plus 1 halves plus n plus 1 halves. Hang on, how do you... Oh my god. I wanted this to be up to n. That's the issue. I was hoping that... Did you do anything besides contest math related to math? I did. So I took a bunch of undergrad courses, so I went through like... But a lot of the basic undergrad courses, like I took abstract algebra, real analysis, so on. I didn't do any serious research. This is lame. I really want to take... I want to make a square such that not too many of the... things only appear once. That's the thing. But I'm not sure I can. I'd have to stop at like n minus 1 quarters. Okay, never mind. We'll just have a trapezoid and it's okay. It's not worth the trouble. Okay, so now let's pretend n is even so I can really just write n over 2. N plus n halves. Okay, so each of the epsilon and I'm gonna for now focus on just the positive bit because I'm curious what will happen. It's possible we will need to adapt and then also use the negative stuff. But maybe we won't. Like, sort of, you only lose like a quote-unquote factor of 4. So, suppose I have epsilon n bad things here. Then every number appears up to n over 2... Up to n times, okay. Up to n times. It could appear up to n, 2n. N. Up to n times, yeah. It can appear at most twice in each column. So certain bad numbers are present. Moreover, among these pairs, at most 0.001 n squared bad pairs in here. So certain pairs are bad and certain numbers are bad. Possibly both. Thank you, Kayasi, for the follow. So in total, at most, like, epsilon plus 1 over 1000 n squared corrupted entries, we'll call them. Thank you, Pikachu, for the follow. Yes, I took real analysis with the author of the textbook. Like, it was Pew. I like his book a lot. So there's at most epsilon plus 1 over 1000 n squared corrupted pairs. A pair might be corrupted if the the pair could be corrupted by either having its number messed up or the entire pair is bad. And this is, on the other hand, this table I have has n over 2 columns. So, and if there is in a column, if I have, as long as there is an uncorrupted pair, that number will be good. So in order to kill off a number, you need like to have at least n over 2 entries. So this gets divided by n over 2. Okay, alright. So that means from between n and 3n halves, there's at most like 2 epsilon plus 1 over. Okay. Alright, so this is getting somewhere now. I feel like at this point I need to optimize. But the basic idea is that I want to do something along these lines. Right now, what I have is I have something like the amount of badness could go up by potentially a factor of, it looks like 4 here, and I wanted to not get that high. I need to, so I did some things that were pretty crude and could probably be improved, and my hope now is I want to try to push it so that the amount of badness does not increase. Right now it's could increase by a constant factor, which is better than what we had before, which is could do whatever I wanted. But I want to, yeah, I want to do better than this. So, okay, that means it's time to bring in the negative numbers, I think. So suppose we have information from 0 up to n. That's not how I want to draw it. So we have control over these pairs. And our working hypothesis is that the number of bad numbers should be less than, I think I want to use 2 different letters because these thresholds might be different. We'll call this one delta. We're also assuming the number of bad pairs is less than epsilon n squared. And what we're interested in is the diagonals. So for example, these are the numbers. This diagonal contains all the entries that have sum n. This one has, okay, so I actually should draw the square bigger. Whatever, it's fine. Yeah, I don't know what the thresholds are, to be honest, but I think there are thresholds. So, yeah, there's a bunch of diagonals. So, the diagonals that will be interesting to me are things that look like this is x plus y is like, I don't know, 3 halves n or something. So, I like to control the numbers between something between minus 2n and plus 2n. Yeah, I think the picture should look something like this. So there's 2 types of things that could happen. It's like we could have a bad pair. There could be just a point that is bad. There can also be a bad number, like say this number is bad. And I want to see what effects that has. So like if this number is bad, I guess the sentiment is that when I have a bad number, there should be some additional bad pairs on, like, this line. Like, if I have a bad number, then on this line, things are going wrong. Like, every point on here either has a bad... Either there is another bad... something. Hang on. Thank you, Anderson STS, for the follow. I wish this picture was bigger. Well, actually, I can just zoom in. How about I just do that? That's too much. Oh man, I never knew how to do art. Wow, this picture is so far off. It's I think the problem is that upper right quadrant is like definitely not a square. It's supposed to... These are supposed to be 4 squares, but you can tell that it doesn't look like a square. Okay, let's just say there's like some number of bad numbers. Then, okay, we're going to pretend this is like at a 40 slope -1. We're also going to pretend this is slope -1. So that's basically the picture we have. There is some number of... Oh, jeez. What a mess. Okay, so we'll say... So there's epsilon... Let's suppose there are delta n bad numbers in -n to n. Then you get these lines. Because they're bad, every point on this line, on the 2 red lines, has to have either a bad pair or a bad something else. I don't know what. So what we're going to do is we're just going to count the number of... Let's just start by counting the number of bad pairs that show up. So our hypothesis, each of these lines, each red line passes through at least n points. So this generates at least delta and each of them generates at least n minus delta n times 2 equals delta minus 1 minus 2 delta bad pairs. So unconditionally, if I have... My head's starting to get in the way. Unconditionally, if I have delta n bad numbers, because each of these lines passes through at least n points, and every point on there needs to either have a bad number or be a bad pair. I always get at least delta times 1 minus 2 delta bad pairs. Wait, hang on. Does that solve the problem? No, that can't be that easy. Does that work? I was about to like do some analysis on the next numbers, but this might be enough. Yeah, so the number of bad pairs is always at most 0.00. So delta is always less than... Oh. Okay, so... Wow, okay, this is funny. But what happens is the statement that we get is therefore... Okay, we got this. So therefore, the number of bad numbers is always between... It's either very big or very small. Either, like, less than 0.01-ish. And, okay, whatever. It's either very small or very big. And then by intermediate value theorem of some sort, the density can't suddenly jump from one threshold to the other. Is that it? Did we do it? I was about to do analysis saying, like, I'm going to use induction to show delta stays small, but I actually think this might just be enough. Did I miss something? I should probably pay attention. Okay, so the argument goes as follows. We draw this picture, this wonderful picture I've shown. And for every bad number, so the ones that f isn't what you expect it to be, I'm going to draw a red line on the corresponding x and y. For example, if there's two bad numbers, I draw like the two red lines, then those two red lines. And then I look at these two red diagonal lines. So on this red diagonal line, every point... If I look at a certain point on here, this is a pair such that x plus y is equal to that number. And because that number is bad, either this point is a bad point, or it could be good, but in that case, it's on a red line. I.e. either the x-coordinate or the y-coordinate is bad. And then you do a double counting argument, where on each red line, you count the number of bad pairs, because there's only so many bad numbers, delta n. And you get this threshold. And you're given that this is less than 0.001 n squared. Always. So since delta starts around 0, well, okay, delta starts at 0, as n increases, the threshold can't suddenly jump, and therefore the the delta is always tiny. Yeah. I mean, I feel like this is going to be a combo problem, right? Because it's like additive combo or something, but definitely combo. What subject? This is combo. Let me be clear about this. This is not a functional equation. I also think it's a very nice result. I didn't think that this counting argument would work out so cleanly. Which problems can we request? Does it have to be from an official math contest? You can request... It doesn't have to be from a math contest. You can request anything that you think makes sense for me to do. What happens is at the start of the stream, so at 8 p.m. Eastern, I fool around for like 10 or 15 minutes while people submit problem requests. And then people vote on which problems they want to see. And then I do the most highly rated problems. Yeah. Alright. Okay, that worked better than I thought it would. Okay, so that is all. Thanks for tuning in. That concludes the proof of this problem, and hope you enjoyed.